Hi, my name is Ferris Wald, and this is my science fair. Van Allen's Key, Unlocking the Secret of Yearly Worldwide Tropical Cyclone Activity. What this science fair tackles is whether or not there is a correlation between solar flare activity and the formation of tropical cyclones. Initially, when I began this science fair, I believed that there was going to be some sort of correlation between the two, solar flares and tropical cyclone activity, based on the research I had done. My basic reasoning is that these solar flares emit tons of charged particles in the form of electrons, which get trapped in the Van Allen belts and gradually precipitate down into the ionosphere. This creates an imbalance, and in order to respond to this imbalance, you have the formation of these tropical cyclones, which wicks these electrons out of the ionosphere. To do this science fair, I had to find sources of data. I had to find both tropical cyclone data as well as solar flare data, and I found three main sources that were very key in creating the science fair. The first one is the Van Allen probes, which were launched by NASA in 2012. What the Van Allen probes do is they look at the Van Allen belts and measure the electron concentrations within them, as well as map the electron precipitation over time. And this will be very crucial later on in my science fair in explaining these nine figures. Another source of data is GOES data, which stands for Geostationary Operational Environmental Satellite. GOES is very important in the science fair because without it, I would not have been able to do both solar flare data as well as tropical cyclone data. So for GOES, for the solar flare data, I use the EXIS system, the EXIS measurement, which looks at X-rays X-ray irradiance per 5 minutes for every year. And I was able to find a website that had the entire year's data for 20 years. And the GOES satellites I used were GOES 8, 10, 15, and the newest and one of the new GOES satellites, 16, or GOES-R as it is called. And this can be seen here. I also use GOES data for solar flare activity. This came from Colorado State University, however. Colorado State University uses the GOES data and sums up accumulated cyclone energy, major hurricane days, and hurricane days per each year, which made my life extremely simple since they summed it already for me. Using these sources, I was able to create my 9 figures. For my abscissa axis, it is plotted on a logarithmic scale and looks at solar flare data. And I have 3 different types of abscissa axes. My first type can be seen in figures 1, 2, and 3, and what these graphs look at is the top 50 flares that were M&S class flares, meaning they had an X-ray irradiance of 1 × 10⁻⁵ watts per meter squared. And I basically just filtered out the top 50 solar flares for each year, summed it, and then used it as my abscissa axis for these 3 graphs. For figures 4, 5, and 6, I looked at M&S class flares for each year from the GOES data for each year from 1997 to 2018. Finally, for figures 7, 8, and 9, I looked at the entire 104,800 data points provided by the GOES data and just used as my abscissa axis for these 3 graphs. For my ordinate axis, I had 3 different types of ordinate axes, and these were not plotted on a logarithmic scale. They were just plotted on a regular scale. And for figures 1, 4, and 7, accumulated cyclone energy was used. And what accumulated cyclone energy is basically knot squared divided by 10,000 not 10,000, and the sum of this and this was summed for each year and by Colorado State University. And this is again for these 3 graphs. Figures 2, 5, and 8, it looks at major hurricane days per year, which is basically how many days of the year had a Category 3 hurricane above. And finally, figures 3, 6, and 9 looks at total hurricane days per year, which is pretty self-explanatory. How many days of the year had a hurricane? And using these 3 different types of abscissa and ordinate axes, I was able to create these 9 graphs. Initially, I decided to do a 1-to-1 relationship, meaning that 1997 solar flare data was plotted against 1997 tropical cyclone data. But there's no correlation, there's no relationship, and there was no relationship. but I refused to give up, and I decided to time shift the data 1 year in reverse, meaning 1997 solar flare data was plotted against 1998 tropical cyclone data, and this created this exponential fit for each of my 9 graphs. The reason I decided to time shift the data 1 year in reverse was due to a previous year science fair which looked at coronal holes and tropical cyclone activity instead of solar flares. And I noticed this time shift approximately 1 year. The fact that I had a time shift of approximately 1 year for 2 different science fairs suggested that that time shift need to be looked into further. It's just not a fluke. And I decided to scour the internet and find possible explanations for this time shift. And this led me to the work of Dr. James Van Allen. Back in 1958 to 1962, he ran a series of tests with the United States military, in which nuclear weapons were detonated in the upper atmosphere of Earth, and Van Allen would measure the electron concentration, would measure the electron decay rates at different altitudes, and plot them in this graph right here. And he eventually discovered this region called the Van Allen belts, which is where electrons get trapped within the magnetic field. And it's between 1.2 to 1.5 Earth radii, and Earth's radius is around 6,300 kilometers. When you look at that region of the Van Allen belt of 1.2 to 1.5, it has a decay. These electrons decay at around 200 to 400 days, which is within that 1 year period, which explains my overall time, my time delay of 1 year. Using these 9 figures, I was able to create a variety of results, but my first one is obviously that there is some sort of relationship between the two. As you can see, for each of the 9 figures, there's some sort of exponential relationship that's occurring. Another result is that it's mainly the M&S class flares that are pumping up the Van Allen belts with these electrons and are pushing it down into the ionosphere. Reason being is if you look at figures 4, 7, if you look at these 2 columns, this one only looks at M&S class flares, while this one looks at the entire gauge data, and there are many similarities when looking at the exponential fits as well as the equations that explain these fits, suggesting that it's mainly the M&S class flares that are doing the majority of the work in pumping up the Van Allen belts. As well, breakout, which is the point in which the entire graph becomes nonlinear, occurs at around 2e to the minus 2, 2e to the minus 3 for figures 1, 2, and 3, and 2e to the minus 2 for these 2 columns right here, 4, 5, 6, 7, 8, and 9. Looking at tropical cyclone activity, a major result is that figures 2, 5, and 8, which looks mainly at major hurricane days, have the best error out of all the data. They had the lowest error overall, which suggests that it's mainly major hurricanes that are responsible for wicking out the electrons from the ionosphere. Even though these 3 graphs had the best error, and the error was relatively low compared to the other 9 figures, overall the error is really, really low. But I was able to find explanations for this error, which will be talked about later in my error analysis. So conclusions. There are many conclusions that can be drawn from this relationship, but my main one is the explanation as to why this relationship is occurring. I researched extensively on this subject matter and came up with my own idea as to why this relationship is occurring. What I believe is happening based on all the research is that these solar flares emit a combination of both X-rays and electrons. The X-rays are high energy and bombard the electrons and cause the electrons to be pushed down and precipitate into the ionosphere. Meanwhile, the electrons are released from these solar flares, cause the Van Allen belts to become pumped and overall expand downward into the ionosphere. The combination of these 2 processes leads to precipitation, and precipitation of electrons downwards into the ionosphere. In order to counteract this imbalance, you have the formation of these tropical cyclones, which wick out the electrons from the ionosphere and restore stability in the entire system. However, system. And this usually occurs along the relationship of an e to negative t over tau relationship, which is used to determine the amount of electrons that remain over time, depending on its altitude. And and overall, this entire process occurs over the period of a year, except when there is a major X10 plus solar flare. When there's an X10 plus solar flare, the entire process is sped up substantially. And this can be seen multiple times, mainly in the September storms of 2017. So, back in September of 2017, there was a major X10 plus solar flare. The last one we have ever had, and this occurred on September 6th of 2017. There was a major X10 plus solar flare, along with 31 other MNS class solar flare events. During that same time period, in September of 2017, and specifically at September 6th of 2017, you see the intensification of Hurricane Irma, along with the formation of Jose, Katia, Lee, and Maria, which suggests that when there's a major solar flare event, X10 above, the process is sped up, and you will see the effects on tropical cyclones immediately. As well, this conclusion about X10 plus solar flares is validated by the October storms of 2003. On October 31st of 2003, there was a major X27 solar flare. Due to the X27 solar flare, they were able to map out. They were able to observe the concentration of electrons at different altitudes during this solar flare event, and notice that when there was this major X27 solar flare, the electrons were pushed down immediately and precipitated down into the ionosphere, suggesting again that the entire process is sped up with these major solar flare events. So when looking at these 9 graphs, it's important to note that, as stated earlier, there's a time shift of approximately 1 year. This gave me the idea that there's a in predicting future year tropical cyclone activity from current year solar flare data. So using GO16 data, I was able to predict 2019 I was able to predict 2019 tropical cyclone activity using 2018 solar flare data. And this is represented by this red dot right here. Looking at that red dot, it appears that we're going to have a really calm or hurricane season in the year 2019. And reason being is that the 2018 solar flare season was really mellow, and there were very little solar M and X class solar flares throughout the entirety of the year. However, if there is a major X10 plus solar flare, the model will probably fall apart. So error analysis. As discussed earlier, I had high error for my entire science fair. And this can be explained for 2 reasons. The first reason is just the way the data was presented. So due to Colorado State University summing up their data for each year, I had to sum up solar flare data for each year as well. This leads to a problem, because if there's a solar flare event at the beginning of the year, you should see its effect on tropical cyclones within that same year, leading to this error, because the entirety of the science fair is based around the 1 year time shift. As well, another cause of the error is X10 plus solar flares, as discussed earlier. As stated earlier, the entirety of these 9 figures are based around this time shift of approximately 1 year. If there's an X10 plus solar flare, you should see this effect on tropical cyclones instantaneously, leading to this error. Looking into the future, I have found many possibilities to enhance my science fair and revise it. And one of the ways includes looking at coronal mass ejections. 78% of these X-class solar flares have an associated coronal mass ejection. In the future, I want to see whether or not these coronal mass ejections correlate with tropical cyclones, and could be the true reason for this relationship. As well, during my state science fair competition, I was informed by one of the judges that there is data called MODIS, which looks specifically at the ionosphere. If I want to also see whether or not MODIS data correlates with tropical cyclone activity. Finally, I want to see whether or not I want to see whether or not I can find data that looks at total electron currents within the Earth's atmosphere, and just apply to tropical cyclones. So, as always, these science fairs are not an isolated event. No one person creates a science fair. It's usually the collaboration of multiple members. Over the course of the science fair, I have talked to numerous individuals who are experts in this field and have helped me create this board and presentation. The first person I would like to thank is my science teacher, Derek Bushman. Derek Bushman has helped me critique my science fair, helped me go through the scientific process, helped me present my data, and has helped me just get format my board and my presentation, and I'm grateful for that. As well, I talked to Mark Parrish, who works at Los Alamos National Laboratory, and he helped me with my statistics for these graphs. Finally, I reached out to individuals such as Brian Tinsley, a professor emeritus at Dallas University, and Dr. Burkpile from UCAR, who commended me, and I met them in person in Albuquerque during a Solar Observers Conference, and I talked extensively to them about my science fair, and they gave me tips and critiques on how to improve it. As well, they commended me for what I'm doing and urged me to continue forward in the future with my science fair. Hopefully, as time progresses, I'll have access to more data, and we'll be able to revise it so that it is more accurate and could possibly in the future be published in some sort of scientific journal. Overall, I just can't wait to pursue this field and see where it takes me. Thank you for taking your time to listen to my presentation.